Hello, Chris, can you hear me? Hello,
Hello, hello.
hi, can you hear me? Hello, okay, okay, I can hear you. And you finished the homework?
Not yet.
Why?
Didn't have time.
Why have a time? You do what?
Uh, Study chemistry.
Okay, mm, let's take a review the last two set lesson, right?
Yeah.
Okay, look at the syllabus and let's take a quick review. Last two lesson, the first lesson we talked about the electrical field, right? Okay. And second lesson we talk about capacitance. So, what is the capacitance? Remember, remember what is the capacitance?
Store charging or discharging.
Okay, yeah. You just mentioned that they have the two process, right? The first process is to charge the energy, right? Charge the capacitor energy. And the second process is to discharge the energy, right? Okay. And we have learned if we charging or discharging, that we have the three different graphs, right? The first graph is the current, related about the current. Second graph is related about the potential, right? Potential difference. The second and final one is really about the quantity, right? Charge quantity. Look at this. Okay, the three graph, right? Okay, and you can tell me the three graph is the process charging or discharging.
This is
Is it charging or discharging?
charging. It's charging.
Discharging. Why discharging?
No, not discharging. It's charging.
Okay, it's charging. Why? Because we can see, and if the battery charge the energy, right? Charge the capacitor. Okay, and we know the current will decrease, right? Will decrease like the exponential decrease, right? Okay, so we can see from distinguish them from the current and time graph, right? Okay, understand that?
Yeah.
And the potential difference and the quantity is the increasing, right? Is increasing because the capacitor will get in the electrical energy, will get in the potential difference, okay? And same time, they will get in the charge, right? Charge quantity, okay? Understand that?
Yeah.
Okay. After we have another charging, okay, and we are going to another discharging energy, okay, like the circuit, the closed loop, the closed circuit, okay, and here's the battery, okay. After battery releasing all the electrical energy to the capacitor, and the capacitor has the full energy, okay, for the electrical energy, for the electrical energy, okay, energy. And if we switch to the point P, okay, or switch to the point Q, okay, and which means collects the point Q, and you can see the right side is like the closed circuit, right? The loop.
Oh, yeah.
Understand that?
Yeah.
Okay, the loop. And here's the loop. And the capacitor has become the new battery. Okay, become the new battery. Okay, become new battery. And to provide the electrical energy to the capacitor that will be dissipated, right? Dissipated by the resistor. Okay, and the ammeter, and we can reading the number. Okay, understand that?
Yeah.
So the process we call it discharge the energy, the discharge. Okay, and the process we call discharge. Understand that?
Okay.
Okay, and here the three graph. The three graphs is related about the discharging process, and we can see the graph like current, potential difference, and the charge quantity, and all are exponential decay. Why exponential decay? Last lesson I told you. And you asked me the same question. Why? Why the three graphs all exponential decay? The exponential decay curve. Think about it.
Because it's discharging, and then the voltage will decrease and the charge will decrease because it's discharging.
Okay, because they are discharging, so the approximately the shape like the exponential decay. Okay, the decrease, right? And I just want to say when the capacitor discharges through a resistor, okay, through the resistor. When the capacitor discharges through the resistor, like the graph, through the resistor. Okay, here's the resistor, through the resistor, and first the voltage across the resistor is high. Okay, at the beginning, at first, the voltage across the capacitor, right, is high. It's okay.
Yeah.
Okay, at first, the potential of the capacitor is high. Okay, so we have the we have the large current flows, right? So we have the large current flows. Okay, and at the moment as the charge leaves the capacitor, and its voltage decrease, right? Okay, as as the charge leaves the capacitor, its voltage decreases, right? Understand that?
Yeah.
Okay, and the lower voltage means a small current, right? So the charge leaves more slowly, and this causes the voltage to drop quickly, right, at the beginning, and then more gradually over the time, right? So we can use the mathematically the behavior flows or exponential decay function, right? So the graph is like the exponential decreasing curve. Understand that? Right?
I'm confused why for charging the current is also decay.
Why the charging is also decay, the potential or the quantity, right?
The current.
The current is that process, the charging part or discharging part?
The charging.
Discharging.
Charging.
Okay. Like you think about it, the graph. The battery, the current will cross the battery, okay? And first, look at the graph. Okay, maybe look at the graph. The graph. At the beginning, the current will cross from the battery, okay? And the battery will flow to the capacitor, the charging process. Okay, understand that?
Yeah.
And we know that the energy stored in the battery is limited, right? is limited, right? At a long time ago, at a long time over, long time over, and all of the electrical energy will flows to the capacitor. Okay. At the beginning, okay, the current is maximum, right? The
Yeah.
current is maximum because the all electrical energy is stored in the battery. So at the beginning, so the current has the maximum, right? Has the maximum, right? Okay. And a long time over, the all electrical energy will flow to the capacitor. So that will cause the battery has the low electrical energy. Okay. So if we have the no electrical energy, the no current, right? So the current that will be the approach to zero. Okay. And in the process, in the charging process, the current flows like the exponential decay curve. Okay, because the current flows to the capacitor. The process, like the charging process, the electrical energy will flows to the capacitor quickly. The charging process, the time is so quick. So the current will decrease so quickly, like the exponential decay, right? Understand that?
Yeah.
Okay. So remember the set graph. The first charging graph, the very particular, the one is the current time graph. Okay, and the other two one, the voltage and the charge quantity, like it's like the charging process, the increase, right? Okay, increasing to the maximum value. And but but the current time graph, like the exponential decay. Okay, and in the charging process, the all three graphs are decreasing exponential decay. Understand that?
Yeah.
Okay. After that, and look at the summary. Look at summary. Okay. The discharging, we can summary that. The discharging curves all identical. All identical. And the current decrease for the charging process, but increases for the potential difference and the charge the store. Okay, so remember, understand that.
Okay.
Mm-hmm.
Yeah. Yeah.
Okay, and look at the new knowledge. That is the time constant. Okay, here's the definition for the time constant. The time constant, like the time for the particular second. The particular second is for the in the discharging process. If we discharging the energy to the one moment, the moment is that we have rest of the 37 percentage of the original value. The original value represent the electric energy. Okay, and and the time constant for the charge current or potential difference in the discharging process. The capacitor, the energy of capacitor decrease to the 37 percentage of the original value, and we call it the time constant. Understand that?
Okay.
Mm-hmm.
Yeah.
Okay. So the time constant is just like the time. It's just like time. The time. The time. The time we define the moment. The time taken for the charge or the current or the potential difference. And the discharging process that will decrease the energy will flow to the other resistor. Okay, flows to other resistor, and will decreases to the 37 percentage of original value. Okay, if the original value is the 100 and then now becomes the 37. Okay, becomes 37, and the time interval the time interval, the process time interval, the changing time interval, we call it time constant. Understand that? Here's the definition of a time constant.
Okay.
Okay, and alternatively, for the discharging, that will the capacitor that will decrease to the 37. Okay, 37 of original value, but in the charging capacitor, the time taking, we call it the charge energy to original value of the 63. Okay, understand that? So in the discharging process, the energy of a capacitor decreased to 37% of original value. Okay, and the charging process, the time taking, the time constant is like the time interval from 37 to 100, right? So the change is the 37, right? And the time taking in charging process, in charging process, we called the time taking for charging, right? Understand it? We call it time constant for charging part. Understand it?
Okay.
Okay, and here's the formula for time constant. Okay, the time constant, here's the formula. Okay, and we use the symbol to represent the time constant. Okay, the unit is the second, and is the product of the resistor and the capacitance. The C is the capacitance. Okay, the Farad unit, the unit is Farad. Okay, and the R is the resistor. Okay, resistor is what? It's like this. The discharging process, the resistor value. Understand that? This one, resistor value. Okay, so if we want to calculate the time constant, okay, time constant, we just need to find the resistor in the circuit or the capacitance of capacitor. Okay,
Okay.
understand? Okay, and for this, the graph, the left side graph to represent the charging process. The charging process, and I just mentioned the energy that will increase by the 63%, right? And the discharging process that will decrease, right? Decrease too. Okay. And here's the increase too, right? And we spend the time, we call it time constant, the time interval. Understand that?
Okay.
Okay. Look for the work example. A capacitor of the 3 nanofarad is the discharge. Okay, in the discharging process, through the resistor of resistance R. Here is the resistance R. The time constant of discharging is this one. Okay, and we want to know the value for the resistor value. Okay, how to do it? How to solve it?
Time constant
From the
equals the capacitance times the resistance. So rearrange the equation to R equals the time over the capacitance.
Okay, so you use the time constant over the capacitance of the capacitor, right?
Yeah.
C, right? So we can get in the resistance. Okay, and take into the time constant is the denominator, and the denominator is the 7 nanofarad, and transfer the unit 7 times 10 and -7 and -9, right?
Yeah.
Okay, so we can get in the final result. Okay, this one. And look at the formula. If you want to go in deeper to understand more the exponential curve is like what? And we want to find the formula is about the exponential discharging in the capacitor. Okay, so and we just mentioned the the curve is like the exponentially decay. Okay, exponential decay. So exponential decay. So we can use the mass formula like this one, like this one. Okay, to use the mathematical formula to describe the exponential decay equation. Okay, so the first we mentioned the charge quantity. Okay, look at the formula. The formula. The Q, the left Q is it means the remaining charge. Okay, remaining
Okay.
is like the moment we have the remaining charge. Okay, and the Q delta is like the initial like the at the beginning the value, right? And this is the Q delta, and this is Q remaining, right? Okay, understand that?
Yeah.
Okay, and here, and we, I want to find the ending point in the time constant interval. Okay, maybe we can find this P1, this one P2, this one P3, and we want to find corresponding the point 3 and getting the charge quantity is what? Okay, is what? Is what? So we can use the formula, the exponential decay equation, okay? And we need to understand this one. This one is like the Q delta times E and the negative T over the R constant times C, right? The
Yeah.
denominator RC is what? Time constant, right?
Oh,
The
yeah,
RC,
yeah.
yeah, is time constant, okay. And the denominator, the T represent the elapsed time, okay? Which means that we have the dissipated time. Okay, if we spend a 2 second, okay, and we can get in, take the 2 second. If t is 2 second, okay, and we can take into, and we can get in. After we discharge the 2 second energy, and the rest of the charge is what? Okay, use the formula. Understand that?
Oh, yeah.
Okay, so here's the formula one. Okay, it's about it's related to the charge quantity, right? Okay, and the other formula is about the potential difference. Okay, or current. Like, and we can call the Ohm's law. Okay, the Ohm's law tells us the potential equal the product of the resistance and the current. Okay, and so if we have the same graph of the potential difference over the time, so we can get in the approximately the same graph of the current over the time. Okay, so the and time and the current obey the same equation of the exponential decay. Okay, so the formula unchanged, but change this one and this one. This one is the at the moment the sum time, the after sum time current. Okay, like the remaining current. Okay, and the I delta is the initial current. And look at the graph. The graph. The current over time graph like this exponential decay. Okay, and we also use the formula to find the rest of the current. Okay, if we discharge 2 second and corresponding the remaining current. Okay, if we discharge the 3 second and getting the remaining current I1. Okay, understand that? I2, I3. Understand that?
Y-
Mm-hmm. So the charge quantity, the charge quantity and the current charge quantity obeys the same exponential decay equation. And I just want to know the potential is also obey the equation, right? Or not? Potential is also obey the exponential equation. This one, exponential equation or not? The
Yes.
potential. Okay, yes, no problem. Okay, look at the work example. If the turn capacitance of the MOSFET capacitor fully charged, that we have fully charged, right?
Yeah.
By the travel power supply, and then we will discharge the resistor. The resistor resistance is 1000 ohm, and we want to know what is the discharge current after 15 seconds. Okay, how to solve it? Use which one formula? Use which one formula? Use which one formula? And we want to know the discharge current. So we might mention the current formula, right? Use which one formula?
Use the
One, right? About
the current, yeah.
okay. So and we want to know after the 70 second the remaining charge, right? The remaining current, okay? So we can use the formula I equal initial zero, okay? And E and negative T over RC, right? Okay. So we know some variable. We have no some variable. Which variable that we have no? Which variable?
The
The one, the resistor, okay,
resistance,
and the capacitance and
the time.
the time. The time. Okay. And how to use the potential? How to use the potential to solve the current in the equation?
V equals IR.
Okay. So we might be use the Ohm law, right?
Yeah.
The potential equal the current times the resistance. Okay, so if we can use exponential equation, decay equation to find to find what? To find at the moment the remaining voltage, right? The remaining voltage, right? Remaining voltage. So we can use the remaining voltage to find the current. Okay, use the voltage, the potential over resistance, right? Understand that?
Yeah.
Okay, so you do it.
12 over 1000.
What? Repeat again.
12 over 1000.
Okay, so you take the variable into equation, right? And the e and the negative 12 over and the 1000 and times the c, right? The c is the turn and times what? The mile-Farad transfer unit.
10 to
Mile-Farad.
negative 3.
Okay, 10 negative 3. Okay, and we can use the other, might be the potential, right? We want to find the remaining potential, so we might use this one. Okay, the initial potential is the 12. Okay, right? So they take the variable into equation, so we find the remaining potential, right? Remaining
Okay.
potential. Okay, okay. And after we have found the remaining potential, so we take this. Okay, we'll take this into the equation, right? Into the equation, okay? The v, okay, not the initial value, okay? And over 1000, right? So we finally we can get the discharge current after 15 seconds. Okay, understand that? Mm-hmm. Understand that.
Okay.
Okay. So the question just tell us how to use the three formula of the exponential decay equation. Okay. At first, after we read the variable, the capacitance, the voltage, the resistance, and the topic just tell us um, to find the discharge current after 15 seconds. Okay, so the first we might think this formula one, right? The first, at first the we might think about the formula one. Okay, but but the we don't know initial, right? We don't know the variable initial current, right? Okay, we can find the initial current, right? Okay, right? And or maybe we can use the Ohm's law to find the initial current. Okay, and I used another method. The first I find the remaining potential. Okay, remaining potential, and I know the resistance is 1000 ohm meter. Okay, and take the variable into. Okay, so finally I get in a current after the 15 second. Okay, understand that?
Y-
Okay, understand that?
Yes, I understand.
Okay, and here is the formula. Look at it. This one. This one. Okay, so the way have to remember the first formula, the Ohm's law. The second formula, the charge process, right? Okay, okay, the charge process, right? And look at it. This one. This one is what? This one, then we will change the exponential decay into the log equation, right? You have learned the math, right? So we can use the formula to change the equation. So how to change the exponential equation into a log reciprocal? How to change this one into the log reciprocal?
Uh, bring the Q0 to the left,
Mm-hmm. And then
and
and
then
then
log both side.
log both sides. Okay, yes. So the both side the will log, right? Okay. The we might use the logging. Why use the logging? Mm-hmm.
To
Why?
cancel out the exponential constant.
Yes. Like the logging e is equal to 1, right?
Yeah.
So it might be more easy. Okay. So we use the logging, right? Okay. So and to transfer into the logging rows, okay? And the logging e and negative t over the RC, right? So we can cancel this one. So we're getting this one, right? Okay. So the logging equation that will become the negative time over the RC, right? Understand that?
Yeah. Okay.
Okay. And the left side is the logging the initial quantity and the remaining quantity, the fraction, right? Okay. And we can transfer into the minus equation. Okay, transfer the fraction into the difference, right? Okay, so use the remaining login charge quantity and minus the initial quantity, right? Login, right? So we can get this one, okay? Understand that?
Yeah, okay.
And we shift the initial value, the constant, to the right side, and we can get this one. Okay, why are we getting this one? Because we want to find the straight line graph, okay? The straight line graph. And this one represent y-axis, okay? And this one, the time t, represent the x-axis, okay? So the form will become the what? Become what? Become what? Become linear
The
equation. Become linear equation. Okay,
oh
the y equal mx plus c, right?
yeah.
The form, right? This form. Okay, and so we can get the m is equal to what in this equation? What is m? The gradient. The gradient.
-1/RC.
Okay, the gradient is -1 over RC, right? Okay, what is the intersection with the y-axis? The c.
ln Q0.
Okay, log Q and the okay. So we can use the graph to find the gradient, right? To find the intercept with y-axis. Okay, understand that?
Yeah.
Okay. So this formula is that we transfer the exponential decay equation into the logging equation. Why we use the logging equation? Because we want um to find the straight line graph, okay? And using a Basel-Field line or the straight line graph to find the RC, right? To find the initial value, okay? So the graph like this, right? Understand? Mm-hmm.
Yeah.
Understand it, right? Okay, so the gradient represent the -1 over the RC, okay? And the intercept with the y-axis value is the initial value, the login initial value of the charge quantity, right? Understand that? Mm-hmm.
Okay.
Okay. So remember the formula, one. And the straight line, the gradient is negative, right? Okay, because here's the negative, right? Understand that? Mm-hmm. So
Yeah.
if I want to find the RC, the time constant, how to use the graph to do it? How to use the graph to do it, to solve it?
Find the gradient.
Find the gradient, 对 Yes. I want to use the gradient. I want to use the graph. The first, I want to use the graph to find the time constant. The first you mentioned that we can get the gradient, okay? And how to use gradient to get what? To get the time constant. How to use the gradient to find the time constant? The gradient is m, right? So m is negative RC. Okay. If you want to find the time constant, so RC is what? It's -1 over m, right?
Yeah.
Okay, so we can transfer like this, right? Understand that?
Yeah, okay.
Okay, understand that. Okay. And look at it, for example. When the capacitor charges, the voltage across it varies with the time t. Okay, and the graph showing the variation. Okay, the y-axis is the fraction, not only not the graph is the charge quantity. Okay, and the x-axis is the time. Okay, and use The topic just want us use the graph to determine the initial voltage across the capacitor. Okay, how to solve it? How to solve it? How to solve it? The y-axis has changed the law in V. The law in V. The V is the potential difference. Okay. So the equation above the graph, here's the equation. Which equation that we might use?
The
This one,
first
the
one.
first. Okay, the first one. That we might use the first one, and the first one is law in V equal the negative 1 over RC, right? And times T, and plus the law in delta. Okay, law in delta V. Okay, so how to use the graph? How to use the graph to find the initial voltage, not time constant. Initial voltage. How to use the initial voltage?
Find the intercept.
Okay, the intercept value is 2.1, right?
Yeah.
What the C represent the line, right? Okay, so and we can use the calculator to transfer it, or my use the initial value is the E, right? And 2.1. Understand that?
Yeah.
Okay. That is rule of the log rules to transfer into the exponential, okay? And the log function transfer into the exponential. Okay, like this. Understand that? The topic. Is there any problem?
No problem.
Okay, so the discharging process that we have transferred the exponential decay into a log equation. Okay, a log equation can be written as the linear string, right? The straight line. Okay, the straight line that we have the gradient and the intercept with y-axis. Okay, so here is the three equation. Okay, the first one and another one is the law in Q, right? Equal the negative 1 over RC and times T, right? And plus the law in Q and delta. Okay, from the three equation, okay, is there any similar that we will find? Is there any similar of the three straight line? Is there any similarity?
All are decreasing gradient.
Okay, the first all decreasing. And how about the gradient? The gradient. The gradient. How about the gradient? Compare their gradient. Is it equal or not equal? The gradient.
All equal.
Yes, ultimately equal. Okay, equal gradient. Gradient value, right? Okay, but which variable is not equal? Which variable is not equal from a graph?
The intercept.
Yeah, different intercept with y-axis. Different intercept with y-axis. Okay, understand that,
Yeah.
right? Okay, and finally, here is the graph that tell us. Okay, to mention it. The first the gradient of the straight line is given by the -1 over the time constant, right? And the second, their y-intercept with the line represent the initial Laurent charge quantity or initial potential difference, right? Laurent, right? And the Laurent initial current, right? Understand that?
Right.
Okay. So this is the chapter, okay? It's the two chapters that we have done, right? And the content, look at the content. Okay. The content, okay? The content is about capacitance. Okay. Quick review. The first in this chapter of the capacitance, we know the capacitance is what? Is the measure how large or how small of the capacitor, right? To store electrical energy, okay? And the second, and we learned the equation for energy stored by capacitor is what? The equation. Use the charge quantity and the capacitor to calculate the energy stored in a capacitor is what? The equation. The energy stored by the capacitor equation is what? You remember?
Forgot.
Okay. The first, the capacity is the charge quantity, right? Over potential, right?
Oh,
Okay. And the energy is the area of the charge quantity over the potential, right? So that is the 1/2 times the Q M V, right? Understand that? Okay. And finally, the form that will change, right? Understand that? Oh, no. Sorry, I mistake. It's not the 1/2 times the Q times the V. It's what? It's C V, right? Mm-hmm.
okay.
Okay, the equation. And the next one is a curve, right? The curve that can be divided into two sections. The first section is the charge curve. Okay, the particular one of the charge curve is the current over the time graph, right? Okay, that is the decreasing, right? And the other two one is the increasing, right? In the charge curve. Okay, and the discharge curve, the three graphs, the current, the potential, the quantity, all exponential decay, right? Okay, and next one is the exponentially discharge in the capacitor. Understand that? And we derive the equation, transfer the exponential decay equation into the linear straight line, right? Okay, understand that?
Yeah.
Is there any problem?
No.
Okay, the final one, look at the core practical. That is the equipment. The purpose of the equipment is to investigate the capacitor charge or the discharge. Okay. Okay. Look at this one. This one, we are going to investigate the capacitor charge or discharge. So the first, we have to know the M of the experiment. The first one, the M is to calculate the capacitance. Okay. Which means we have to calculate the C, right? The Fred. Okay. And here's one example of the how to construct the practical. Okay, the first we have to find the variable. Okay, if we do the equipment, the first that we have to find the variable. Okay, right? Right.
Yeah.
Okay, the first, the variable, the includes the time. Okay, the second one, the dependent variable is the potential difference. Okay, and here is the control variable. Control variable is really about the resistance of the resistor and the current in the circuit. Okay, here's the equivalent list. The first, the apparatus that we need is the switch, and the purpose is what? To switch between the charging and the discharging circuit. Okay, and the second one is capacitor. The capacitor, that means the purpose of the experiment is to calculate the capacitance of the capacitor. So we have to this one, right? Have this one, okay? And another one is the resistor. The resistor that we choose the larger one, the 10,000, right? And the purpose is to discharge the capacitor. Okay? Understand the apparatus and the purpose, meaning understand. Okay. And the next one is the battery pack. And here that we need the voltmeter and the stopwatch. The purpose of stopwatch is to measure the time taking for the capacitor, okay? That convenient for us to calculate the time constant. Okay, calculate the time constant. Okay, and here's the resolution. Okay, the resolution to us to reduce the error, okay? And here's the method. Okay, the graph like this. Okay, so I just want to know if we switch to the x, and they will become what? Switch to x, they will become what? Mm-hmm.
Charging.
Yeah, there will be the charging. Okay, there will be the charging process. Okay, if we switch to the y, okay, there will be what?
The discharge.
Discharge. Okay, understand. Okay, discharge. And in so the different switch, right? Different switch to the different point that we have the different process. The previous this one is the discharging is the charging process. Okay, the current flows to the capacitor. Okay, is to discharge the is charge the capacitor. Okay, and after the energy dissipated by the capacitor. Okay, the way switch to point Y, and the process will become a discharging process. Okay, and we need the voltmeter to measure the initial potential. Okay, right?
Yeah.
And we use the voltmeter to measure the initial potential of the capacitor, so we can plot the initial in the discharging process. The curve like this, right? The V, the T, so it's the initial. So it's the initial value. Okay, initial value, and use the initial value. Okay, and here's the resistor to dissipate the energy of from the capacitor. Okay, understand that? And the next step to set up the data, right? Use the stopwatch to record the time. Okay, use the voltmeter to measure the initial or different potential difference, right?
Yeah.
The different time corresponds to the different potential difference, right? Okay, okay. So finally, that we can use this equation to analyze the results, right? Okay, and here's the decay equation, right? Exponential decay equation, right?
Yeah.
Okay, and the transfer, if we transfer into the linear straight line, okay, and here's the ln v equal the negative t over rc, right? And plus, right, ln initial, right? Understand that?
Yeah.
Okay, this formula help us to analyze the result, and after that, then we can plot the graph like the linear form, the graph like this. Okay, the y-axis is potential, the axis is the time, okay? And the line will be what? The exponential curve that will transfer into the linear. The y-axis is ln v, the axis is t, right? And here is the, okay, here is the linear line.
Yeah.
Understand? The y-axis is the initial value. Okay, the gradient equal -1 over RC, right? Understand that? Right?
Yeah.
Okay, no problem.
No problem.
Okay, so this is the one of the example that we use the potential difference and use the time, use the charging process or discharging process to analyze the results and transfer the exponential decay equation into the straight form, right? And we use the straight form to easily get the initial value, okay? To easily get the gradient, okay? And finally, if we want to find the time constant, okay? That we find the time constant, the equal is -1 over gradient, right? Okay, and time constant is the product, the capacitance C, and times resistor, right? And transfer. The equipment purpose is to ask us to find the capacitance, right? So that we use the -1 and the gradient and times the resistance, find the value, right? Understand that? So this is the results. The finally we get the capacitance, right?
Yeah.
The capacitance of the capacitor. Okay, understand that?
Yeah. Understand.
Okay, so the chapter relate about the capacitance and capacitor and the charging process, the charging parts, the difficult part, the most difficult part that we have learned. Okay, and here, here is the homework. Okay,
Okay.
and I will send you down, right? If you are down and you send me, okay, understand that?
Yeah.
Okay, and I have a question. The next time that you are available for studying is what? And how's your plan for your examination?
So maybe let me see. Maybe tomorrow.
I mean, we need to make a plan, right?
Yeah. Yeah. Yeah.
Because the examination is approaching, right? And we
Yeah.
need to, okay. And how about your further math and your chemistry?
I don't have further math. Only math.
Oh, you only math, okay?
Yeah.
Okay. How's your math?
Math I didn't revise for a long time, but chemistry I'm revising right now.
Okay. So you might have the difficulty in the math, right?
Yeah.
Mm-hmm.
Yeah, I might, uh, because right now I didn't touch math yet.
Okay. Or maybe next time that we can analyze the math that you have learned, right? Okay.
Uh,
So let me think. Um, the I mean, we will to make the plan or the timetable, right? And I will use the Excel to make a timetable for the every time that we planned the lesson and what we are going to finish and what is the marking time. Okay.
yeah, okay.
After I talk about you the timetable, and I will make the schedule, okay, and the
Okay.
in the group, and the way every time the lesson and the exact time that we use the schedule to act, right? Okay,
Yeah, okay then.
okay. So here's the homework, and I will send you, and you have to finish it, right?
Yeah, 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 I'll finish it.
Okay. Bye bye. So today's lesson is over.
Okay, bye-bye.
Bye bye.
Thank you.